Aditya was asking me something about the whether the pressure change can remain zero, right? That was your query, right?
Oh, yes, sir.
Yeah, actually the thing is that the
So,
pressure, is that
is
okay?
it
Clear?
cumulative over that time?
No, we were talking about the tendency of the pressure, not the absolute pressure. We were talking about the tendency, pressure tendency, right? Change
Yes,
in
sir.
pressure. Actually, the pressure has a diurnal variation that you must have studied earlier. Did you study diurnal variation of the pressure? Pressure, if you just surface pressure, if you plot 24 hours hourly variation, then it looks like this. Have you seen this diagram? Or can you see this diagram?
Yes,
Yes,
sir.
sir.
Yes,
Yeah,
sir.
this is the diurnal variation of the surface pressure. Okay, and you can clearly see that there are two minima and two maxima in the diurnal variation of the pressure, surface pressure. This is, see, the two minima is one at local time 4 o'clock in the morning, another one is 4 o'clock in the afternoon. Okay, and the two maxima, one is at 10 o'clock in the morning and the other is at 10 o'clock in the night. Okay, so this is the 24-hour variation of surface pressure, diurnal variation of the surface pressure. And we see this diurnal variation, there is two minima and two maxima, and that occurs because of the atmospheric tide, right? But what we were talking yesterday is the change in surface pressure because of the movement of the system, atmospheric systems. Okay, the anomaly caused because of the movement of the surface pressure, right? So that anomaly is superimposed upon this diurnal variation, right? That anomaly is superimposed upon this diurnal variation. So in other words, so when there is no change in the surface pressure tendency, that means the surface pressure tendency is zero, right? Say, this is one of the observation, regular observations collected by all the Met Observatory, that what is the surface pressure tendency in the last 24 hours. Say, generally this is done at 8:30 in the morning. That means 3 GMT, 3 UTC, right? Local time 8:30 in the morning. So local time 8:30 in the morning, all the Met observers. हेलो हेलो हाँ जी हाँ ठीक है तो वहाँ पे सिक्योरिटी गार्ड को दे देना नहीं नहीं कहाँ पे हो तुम 1 नंबर गेट पे हो ना हाँ तो गार्ड को दे दो हम आकर के वहां से ले लेंगे अभी हम हाँ सॉरी कैन यू हियर मी
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Sorry, there was interruption. So I was saying that all the Met observers are supposed to collect observation of the pressure tendency, the last 24-hour changes in the pressure. That means whatever was say pressure yesterday morning at 8:30, and what is the change today at the same time 8:30 in the morning, that is supposed to be reported as part of the regular observation. That is the pressure tendency, right? And that pressure tendency may be zero if there is no change in surface pressure. No, from yesterday at 8:30 morning to today at 8:30 morning, that means the pressure tendency is zero. Okay, but if there is change in pressure, it may be positive or it may be negative. And that positive or negative pressure change, that means that isolobar, would indicate now whether the pressure is going to increase at this place or pressure is going to decrease at this place. That's what we were discussing yesterday. And that is one of the very important analysis, the surface charts now, which meteorologists have to do every day, especially in earlier days when there was no NWP model. There was one of the very important chart people used to analyze, and then based upon that, and also other factors, they used to draw inferences that what would be the weather the next 12 hours or 24 hours. So is that clear now, Haridasri?
Yes, sir. Yes, sir.
Okay, okay,
So
fine. So
I read it on Google that pressure tendency is calculated over 3 hours. So that's
yeah,
why
yeah,
I
yeah,
got
yeah.
confused. Yeah.
Okay, pressure tendency can be also over 3 hours. That is not an issue.
Okay.
Pressure tendency means rate of change of any
Mm.
quantity and in the given time period. So somebody wishes to calculate the pressure tendency in 3 hours, that is also fine. But the standard things are no, generally standard things are 24 hours because
24
in
hours.
net there are certain standard things which have to be measured, and that is one of
Okay.
the standard thing that what is the pressure change in 24 hours. Okay,
Okay, sir.
right. So having said that, now let us continue from what we were discussing yesterday. All right, and yesterday we're talking about um, okay, we're talking about this diagram that is the oscillation in surface pressure in the initial few hours. Okay, this is the mean variation of the pressure, and this is the oscillation. And this oscillation is caused in models, especially those models which were not initialized properly, or in those models in which we don't do any data assimilation. In those models, now this is kind of oscillation which takes place, and that's called the spin-up problem. And this spin-up can be so serious that it will mask all the important solutions of the model. And then what we get, the result is all absurd or junk. And that's what Richardson had the problem initially when we got the pressure change of 145 millibars in 6 hours. There was a problem because there was a lot of gravity waves oscillation. The surface pressure was varying because of the gravity wave oscillation. So when such things happen, or used to happen earlier, then people devised many techniques how to filter it out. And then they started talking about the initialization of the model. Okay, and there were several techniques of initialization based on several mathematical processes. Um, One of them was called normal mode initialization. Other was called the non-linear normal mode initialization (NNMI). What you see here is NNMI. People used to talk about NNMI. Then people also started talking about how to filter it out. So they're different, and they tried to design different types of filters, the so-called time filters, robot filters, etc. So these are the filters or the methods of smoothing, how to smoothen the result. These are the methods of smoothing results which Richardson devised in those days. Okay. In fact, in his book, he has devoted one full chapter on this smoothing. Okay. So he outlined 5 smoothing methods. One was the space means taking the mean over space. That means you would take the mean over certain grid points, maybe uh, centered upon your location of interest. You would take, say, 4 grid points around that, or sometimes 9 grid points also around that is taken, and then take a space mean. The other is the time mean. Okay, you take the time mean, say, mean of the last 1 hour, mean of the last 3 hours, and so on. Then there are other methods also known as potential function, the stream function, the smoothing during the forecast, and so on. Okay, so Richardson's Richardson used this method B, the time mean, is a close cousin of the digital filtering, which nowadays people use or people used to do for the initialization, so-called digital filtering. Okay, in which they would filter all the unwanted oscillation, the artificial oscillation. You have seen that the pressure should vary smoothly. Normally, there are no variation of pressure should be very smooth, two minima and two maxima during the 24 hours period. And superimposed upon that, there can be an anomaly which can occur because of the movement of these pressure systems, right? But other than that, pressure should not oscillate, and if it oscillates, that is because of the numerical problem in the model. And that is, although actually if the model is perfect, that would not happen. But because the models are not perfect, no model is perfect, therefore we apply some types of artificial filtering, smoothing, and one of them is called the digital filtering or initialization. Okay, so that's what Richardson started doing that from his days. And this diagram, is this diagram clear? It shows the forecast without filtering and forecast with filtering. Can you see this diagram clearly, or this is too small for you?
Sir, it's too small.
Too small. Okay, if it is too small, then what I will do is I'll just enlarge it artificially here, and if so, then I will just show you like this one. Okay, so can you see this diagram now? Enlarged, but wait a minute. This one, this one. So can you see the diagram now? Better?
Yes, sir.
Yeah.
Yes, sir.
So you can see that in this diagram, this is surface pressure, shortening forecast of sea level pressure. Okay, from an uninitialized, unfiltered, okay, forecast, and the controlled intervals are for millibar, 4 hectopascal. Okay, so you can see it's lots of circles, gola, both are kings as well. You see that kings, so many kings. And these kings or the oscillations are because they are unfiltered. Now, if you see the next diagram, here. Now, can you see this diagram clearly?
Yes, sir.
Yeah. Now you can see
Yes,
that.
sir.
Yeah. So same filled the surface pressure, the sea level pressure. Now after filtering, after smoothing, see all these kinks, now all those small ripples now which were visible in the previous picture, they're all now filtered out. As the pressure is very smooth here, right? So this is what is the effect of the filtering. Okay. So this is what Richardson applied in those days. Okay. So now I move to the next one. So some other crucial advances which took place between 1920 to 1950 are, for example, the better understanding of dynamic meteorology, in which now people understood the Rossby waves in a better way. The quasi-geostrophic theory was developed. The baroclinic instability, people understood what is the baroclinic instability, what is the difference between barotropic and baroclinic instability. Then people also developed different numerical methods, numerical analysis techniques. People understood about the CFL criteria, right? We have studied earlier. Then also along with that, simultaneously the atmospheric observations also improved, right? And radioson was discovered. Now radioson instrument through which people could take the measurement of the vertical profiles of the atmosphere. The electronic computing developed, and the first electronic computer that was developed at the time for the purpose of the forecasting was the ENIAC, right? The von Neumann's laboratory. Okay, so the electronic computer project was the idea of Dr. von Neumann in 1946. Weather forecasting was par excellence as a scientific problem suitable for a solution using a large computer. And the objective of his computer project, was that to predict the weather by simulating the dynamics of the atmosphere using a digital electronic computer. Because before that, now in the days of Richardson, people used to do all those calculations of the parallel processing which we discussed yesterday, about 64,000 processors and so many people. They were all doing the calculations by hand. Even the calculator, the electronic calculator, which are existing today, were not there. So whatever calculations were made in those days were all done by the hand. So von Neumann felt that if you want to really forecast the weather numerically, and that too on time, to be able to use it operationally for public, then we must have a computer. Without computer, the equations cannot be solved in time. So he developed this project to develop a computer. Okay, started this project. And this is what his computer looked like. The first computer of the world, the ENIAC computer, developed by von Neumann's laboratory. It was the first multi-purpose programmable electronic digital computer. It had 18,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, 6,000 switches, and it required power of 140 kilowatts. See, this is the first computer of the world, which was developed by one Nuance project and solely for the purpose of weather forecasting. And you can just imagine how this computer looks like. Is covering the whole hall of the building. One full hall of the building is covered by this computer, consisting of all these vacuum tubes and resistors, capacitors. And you can imagine in today's time, the power of this computer is just in our handheld, palm-held calculator. That is the difference between today and say something like 60, 70 years ago, right? So this was the ENIAC computer developed by von Neumann for forecasting the weather. Now, simultaneously, the meteorology project also evolved. Okay, and they divided into three categories. Plan A was to integrate the primitive equations, which consists of all those dynamical equations like equations of motions, right? Thermodynamic equation, the moisture continuity equation, the mass continuity equation, the hydrostatic equation, and so on. Okay, the problems similar to Jordan's would arise. Then in the second part, people also simultaneously worked about the baroclinics quasi-geostrophic model. We have studied about the quasi-geostrophic model, right? Last semester. You remember that?
Yes, sir.
Yes, quasi-geostrophic model. So there was another group of scientists who were also parallelly working on quasi-geostrophic model for the baroclinic system and how to integrate that quasi-geostrophic equation, but it was too computationally demanding, right? Something like similar to the primitive equation model, also too computationally demanding. And the third group started solving the barotropic vorticity equation. We have also studied the barotropic vorticity equation last semester. Remember that?
Yes, sir.
Barotropic vorticity equation, right? Yeah,
Yes.
the rate of change of absolute vorticity. No, in this equation, zeta plus f, where f is the Coriolis parameter, is conserved. The absolute vorticity must be conserved. dy dt of zeta plus f is equal to 0. Conservation of the absolute vorticity, this is what it says. So another group of scientists, they started working on solving the barotropic vorticity equation. And this is a very simple method compared to the solution of the quasi-geostrophic model. It provided quite satisfactory results, especially for the mid latitudes in those days. Right? And these are the stalwarts of those days. We have seen their photos yesterday, day before yesterday also. The Jules Charney, Isolde Ford, Toft, and von Neumann, 1950s. So they together worked on the numerical integration of the barotropic vorticity equation. Numerical integration of the barotropic vorticity equation, and published the paper in TELUS, one of the very good journal, TELUS, studies journal. So they are the people who started solving the dynamical equations on the computer developed by von Neumann, the ENIAC computer. Okay, so they are the stalwarts. You have seen this photo also yesterday, right? Charney had Lagrange and von Neumann. So the Chardson's reaction after all that was that he was quite happy, obviously, because after so much of effort, he had not succeeded in predicting the surface pressure. And so obviously he was quite happy when all this development took place. And then he wrote a note, he reacted saying that, allow me to congratulate you on the remarkable progress which has been made. And this is an enormous scientific advance on the result in Richardson 22. This is what is mentioned there. So when the NWP developed, then along with the development of the NWP, people started using this for various purposes besides the operational day-to-day weather forecasting for the public. People started using it for the Air Force, air meteorology activity, air services, the naval activities on the ocean, because in those days suddenly when the ships were sailing, they would encounter a very rough weather. Sometimes in the cyclone, they would not know that they are heading towards a rough weather on the ocean. So the Naval Weather Service started, the Air Weather Service of the US Air Force started, the US Weather Bureau for the public, they all started at the time. As soon as they were able to solve the equations numerically and establish the numerical weather prediction techniques. So the Joint Numerical Weather Prediction Unit was established in July 1st, 1954. Okay. Operational numerical forecasting began in May 1955 with a three-level quasi-geostrophic model. Still, they were not daring to solve the primitive equation model at the time, because primitive equation model solution is more dangerous thing. Now, landing into more trouble, more problem. But still, at the time, most of the physical parameterizations were unknown. They were not knowing that. So they felt more safe in solving just the quasi-geostrophic model, and they developed a three-level quasi-geostrophic model. Okay, you might recall that in last semester when we were discussing the quasi-geostrophic model, we were saying that generally we apply it at the middle of the atmosphere and that is at 500 millibar, right? Remember that quasi-geostrophic model. But just applying the model at only one level may not give the accurate result. So they did it for three levels because they have the computer, whatever computer now in a very primitive form, right? So this was the development in USA. Okay, are you all listening to me? Able to hear me?
Yes, sir. Yes, sir.
Yes, sir.
Yeah. So also in India, of course, we started much late. In USA, they started in mid 50s, 1955. But in India, we started much late, sometime in 1980. Okay, in IMD. We started the NWP activity in IMD in 1980s. It all began under the leadership of Professor Dr. P.K. Das. He was the DGM, Director General of Meteorology of IMD in 1980s. And Dr. H.S. Bedi was his colleague in IMD. Dr. M.C. Sinha was also their colleague in IMD. So these people, Dr. P.K. Das, Dr. H.S. Bedi, Dr. M.C. Sinha, they started NWP in IMD in 1980s. But that was again in a very primitive form. They were not solving really any big model or global model. They were only trying to solve a very simple quasi-geostrophic models, one single level quasi-geostrophic model in those days. And the forecast was mainly done by the synoptic method, the old ancient method. It was not really done by the NWP model, quasi-geostrophic model. It was only started to just develop the skill learning processes, the NWP in IMD, and they were not applied really for forecasting. Later on, when it matured slightly more, then they started just taking this as a guidance, the output of the QG model. The IMD started taking as a guidance, but not really for day-to-day operational weather forecasting. And later on, some of the scientists from IMD, they were sent for training at FSU, Florida State University in USA. You might have heard about Professor T.N. Krishnamurthy. Have you heard of him? T.N. Krishnamurthy. No? Nobody? No. Well, T.N. Krishnamurthy was one of the very prominent Indian scientists. He settled in USA long ago, 1950s. Actually, he graduated from Andhra University, did his MSc from Andhra University, and then he did his PhD from University of Chicago in 1950s, and then settled in FSU, Florida State University in USA. And there, because he was doing a lot of dynamic meteorology research on NWP, etc., the development of limited area models. So people from India used to go to FSU to learn from him the NWP, the limited area model. So many of the people, H.S. Bedi, M.C. Sinha, they all were sent by IMD to FSU to learn about the NWP. And after their training, they brought from there one version of the so-called LAM, limited area model, and that was implemented at IMD. And then they started working on LAM, limited area model, for many years in IMD. And that too, just for taking the kind of some sort of a guidance, not really to totally depending upon that now for day-to-day forecasting was just one for the learning purpose and other for the taking as some guidance because not many things were developed in those days. Even the IMD's computer was not there. They had a very simple old type of computer called cyber. You might have heard about the cyber in those days. And then slowly they changed to IBM probably. IBM also very primitive form of the IBM 360. So that's what was the situation in IMD. In fact, when we were doing PhD in IIT Delhi at the time IMD had this IBM 360, and then IIT Delhi we had ICL, British Computer, and then the government of India, purchased one big computer for NIC. NIC was established during that time. Have you heard of the NIC? The National Informatics Center. Have you heard of that? NIC? Yes.
Yes,
Okay.
sir.
Yes,
Yeah,
sir.
good. So NIC was actually established around early 80s in India.
Yes,
India.
sir.
And NIC then bought the biggest computer in India for that time. There was the cyber. Okay, and then from IIT we used to go to work for the cyber, and that the cyber machine of NIC was almost like 6 to 7 kilometers away from IIT Delhi. So we used to just go every day in the evening, and we were given some special permission to run our model in the cyber machine. So we felt the difference, how difficult it was to run in the small, computer system of IIT at the time, and then suddenly the models or the equations that we used to solve overnight or taking a whole night in IIT Delhi's computer, that used to get solved in just few hours in cyber computer in NIC. So there was the days when people in India were just trying to work or learn about the NWP model, but still not many things were available. Like the data assimilation technique was not known, the automatization process was not known. Even the computer graphics, so beautiful graphics are nowadays are available. Those things were not there at that time. Actually, when we were doing PhD, nothing was there. There was like a desktop computer, and there was no graphics. And in fact, we had the card system. You might have heard about the card system, or maybe you might have read in the books that we used to punch card to write a program, one-line program or Fortran. To write the program, we had to punch card in those days and give the cards, deck up the cards to the computer system people. We were not allowed to go into the computer system room. We used to just give our cards to them, and then they used to put the cards in the machine and then read our cards, and then accordingly the program used to get run. So there was the time then, good old days. Subsequently, in 1989, when NCMRWF was established, Research Center for Medium Range Weather Forecasting, under the DST, Department of Science and Technology. From that time onwards, we started working on the global model, and then trying to work for the objective analysis, trying to work for the data assimilation. In fact, initially, because I'm now talking about the development of NWP, the history of NWP in the world, so I thought, I can share you also some old, days, work which we used to do in India. So what we did was for NCMRWF, we somewhere we had to start, right? And then because the rest of the world had already done quite a good amount of work, so we could not start from the scratch, but we had to start from where people were already working at the time, right? And therefore, we borrowed one model, rather two models we borrowed. One from the NCEP, and at the time NCEP was using again two different models, and their model was global spectral model, and one model was having the triangular truncation resolution spectral model, and the other one was R40 rhomboidal truncation. You have studied about these things, right? Do you remember?
Yes, sir.
Yeah, the spectral modeling which we studied last semester for the discretization, right, techniques. So most of the people, they were working with the spectral model at the time in the world, and as you studied in the last semester, the spectral model can be of two types: triangular truncation and rhomboidal truncation. So we brought one rhomboidal truncation model called R40, the 40 waves in wireless space. And simultaneously, we also got another model from ECMWF at the time, and it was the T79 model. T79, the triangular truncation at 79 waves. So those were the two models we borrowed from, one from Europe and one from America, and then try to establish that NCMRWF, install at NCMRWF. We also got a data assimilation system. Initially, it was from the NSEP because ECMWF, they did not give us their data assimilation system because they said that this is a proprietary of 24 countries. The ECMWF is a group of 24, 25 European countries. And so the ECMWF said that because India is not a part of Europe, right, and we are not the member of the ECMWF, so they cannot give their system. That's what they said at the time. But NSEP, of course, they gave us their system, data assimilation at the time. So we started with the simple data assimilation system of that time from NSEP, and the two models, R40 and T79. And then gradually we perfected ourselves in those two models, and then started, making experimental forecast. I still remember those days, in MCMRWF, because things were not automatic. And you might have seen maybe in the photos or maybe in the books those days, there was no hard like what exists today. Like you can carry in your pocket 1 terabytes of hard disk, right? And your pen drives itself has a capacity of like 32 GB or sometimes even more. In those days, those things were not there, and we had a big magnetic round tape. I don't know whether you have seen those round magnetic tapes, big round circle tapes, quite heavy. So the data used to come to IMD every day from different parts of the world. Those data were put into the magnetic big tapes, and then we used to physically carry those tapes from IMD to NCMRWF every day, because there was no communication like telecommunications that we have today, that fiber optics line and all that things. Those things were not there. So those things were manually carried from IMD to NCMRWF. Then decoded, data were decoded, quality control, assimilated, and things like that. So that's how the NWP started evolving in India, and then slowly, it took us about 5 to 6 years to make it operationalized, operational model run. We started, I think, sometime in 1995, regularly on regular basis, daily, everyday data assimilation, everyday model run for 7 days. Initially, we started running the model for 7 days, and then we used to produce outputs by all those automatic graphic softwares, the graphic machines. There used to be very big charts, not like today's. You can just quickly print a A3 or A4 size paper of the graphics. There used to have a very big plotter, like big size telecom printer plotters. So we used to plot charts, outputs of the model in those big maps, and then he used to carry to IMD to give it to them so that they could use it as some kind of the guidance. So for many years, initially, almost like till early 2000, IMD did not trust us. They used to say, we are getting some outputs from model, but we can't completely depend upon that outputs. And they continued their old method of synoptic forecasting, manual forecasting in IMD. But gradually later on, when we improved the model, increased the model resolution, improved the data assimilation technique, the quality of forecasting improved, and then after that they started seeing that our outputs are quite good, right? And then they started believing, and then slowly, they built up their confidence on us, on the NWP product of the model, and then slowly they became completely dependent upon us. Like today, IMD completely depends on all the model products, whether it is from NCMRWF. After that, of course, many things happened. IMD also had its own global model. NCMRWF has now presently the UK main office version Then IITM also was given this task because IITM was supposed to be a research institute, also trying to develop all these things. So many things happened because IMD is supposed to be responsible for the day-to-day operation of the forecasting, and they said that we don't have enough time to really develop these data assimilation methods and modeling techniques. So Now, this has to be done by either NCMRWF or IITM. And because we all three belong to MOES, of course, at the time, MOES was not there, it was the DST, the Ministry of Science and Technology. So, now when the MOES started, in almost like probably it started sometime back in 2006 or 2008, MOES was established. It was separated from DST. So then MOES said that, okay, all the research and development part of the model will be done at ATM, the data distribution part, and the physical processor also will be done at NCMRWF, and IMD will just use the products for their day-to-day operational weather forecasting, and IMD will become the public interface for the weather and climate outputs. So that's how is the story of NWP evolution in India. Okay. So now again going back to 51, Charney in 51 wrote that the outlook for numerical forecasting would be indeed dismal if the quasi-geostrophic approximation represented the upper limit of attainable accuracy. For it is known that it applies only indifferently, if at all, to many of the small-scale but meteorologically significant motions. Right? I mean, we could not depend fully on those quasi-geostrophic models because they had its own limitations. Now, if you just try to analyze carefully the quasi-geostrophic model that you have studied in the last semester, you will see that now it has its own limitation, right? Quasi-geostrophic model. Even if you apply it at 2 levels or 3 levels, eventually you are assuming that the absolute vorticity, the rate of change of absolute vorticity, either it is conserved or if it is changes because of the effective processes, right? So it has its own limitations. Therefore, people knew that eventually they have to use the primitive equation, right? The P model, the full-fledged form of the equations that govern the atmosphere, right? But at that time, they had limitations because they did not know about the parameterization of physical processes. They did not have the good computer. All that they had was very primitive for the computers. So practically, it was impossible to run a full-fledged global primitive equation model, right, for operational forecasting. But later on, when things developed, then all these things were started. People started using that. So all modern NWP centers have abandoned the QG, the quasi-geostrophic equations for operational forecasting. However, they are invaluable for theoretical studies for understanding purposes, right? Okay, now let's talk something about the parameterization. Just trying to summarize the history of NWP. So we have to talk about these things a little bit, although that in this semester, in this subject, we will talk in detail about all these things later on. So parameterization, okay, and then people started realizing that unless they parameterize each of those physical processes that occur in nature, in the atmosphere, the solution of their equations are not going to be correct, right? Because the small scale physical processes cannot be represented explicitly in computer models. Because of the one reason is because of the coarse resolution. The resolution of the model in those days used to be very coarse. The grid resolution used to be something like 5 degree by 5 degree latitude longitude. That means 500 kilometer by 500 kilometer because of the computer limitations and of course understanding of the small scale subgrid scale processes. So they knew that on that coarse grid, even the climate model in those days used to be quite coarse. Weather forecasting models started becoming more finer resolution, like they came down from 5 degree to 2.5 degree, that is still 250 kilometer resolution roughly, then to 100 kilometer and so on. But even at 100 kilometer also, to be able to resolve explicitly different physical processes which occur at very small scale was not possible. So they realized that they must parameterize the effects of subgrid scale processes, and then in that process, then slowly they started developing different schemes, like how to parameterize the condensation in the grid point models, Corther model, how to parameterize the solar radiation, which actually occurs or takes place at a micro scale, the long wave radiation, the short wave radiation, the orographic effects, the land atmospheric interactions, the ocean atmospheric interactions, turbulent transfer of momentum and heat, and so on. Right? So this is how people started gradually, developing, realizing their importance, and then trying to test into the models. So after having said the physical parameterization, then let's talk a little bit about the data assimilation. Because as I said, and as you know, the NWP is a initial value problem, right? I talked about that. NWP is a initial value problem. That means we must have very accurate initial condition of the model, initial condition of the atmosphere. And that initial condition comes from the observation, the current observations of the atmosphere, right? So when people didn't have good telecommunication network, now we'll talk about the telecommunication network maybe in the next lecture, or the GTS, etc., which is used now globally to exchange the meteorological data all around the world. That started after the establishment of the WMO, right? The WMO, when it was established, then they tried to unify, coordinate between different meteorological services of the countries, and then after that, they started telecommunication link called GTS. We'll talk about that later in detail. So before that, before the existence of the GTS, people used to initialize the model. I just mentioned today in the beginning that we used to have the so-called NNMI, the non-linear normal mode initialization, the dynamic initialization, etc., etc. So they were initializing the model to suppress the oscillation in the first few hours to avoid the spin-up problem. But later on, when the communication improved and people also developed the data assimilation technique, then they started simulating the data, the real-time data which used to come every day, which comes every day on real time, around the clock. Then that started getting ingested in the model. And that is the data assimilation. So the model integrates the equation forward in time, starting from the initial condition. In the early NWP experiments, hand interpolations of the observations to grid points were performed accurately. Even we used to do that hand interpolation as a practical class when we were studying MSc meteorology in those days. Now, in practical classes, we used to interpolate by hand to do the objective analysis. These fields of initial conditions were manually digitized. The need for an automatic objective analysis quickly became apparent. Okay. So then there is another important issue here. The data available are not enough to initialize current models, especially a few years ago, especially before the advent of the meteorological satellites. There were hardly any data about the remote places, about the ocean. So there was one big problem to initialize the model. How to initialize when there is no data gap reasons. Okay. Then the modern primitive equations models have a number of degree of freedom of the order of 10 to the power 7. So for a time window of plus minus 3 hours, there are typically 10 to 100,000 observations of the atmosphere, 2 orders of magnitude less than the number of degree of freedom of the model. Moreover, the distribution in space and time is very non-numeric form, non-uniform in space. Therefore, it is necessary to use additional information, okay, denoted by the background, so-called background field or first gauge field, which we get from the previous 6-hour forecast of the model. Then, based upon the background field of the first gauge, we try to objectively analyze the data which comes from the observation. Then we also use a short-range forecast model, which makes the 6-hour forecast, for example, which is used as a first guess in operational data assimilation technique. So the data assimilation has a 6-hour cycle. The large-scale data assimilation has a 6-hour cycle. Even today also, the same 6-hour cycle is used at all places around the world, including at NCM RWF. So this is how the data assimilation is illustrated in this flow diagram. Okay, and what it says is that at different time intervals, usually 6 hours, 0 UTC, then 06 UTC, then 12 UTC, all the observations that come, that is analyzed analyzed, that means that is interpolated onto the model grid. Okay, then that is initialized, or we assimilate that using the first guess background. We shall talk about this further in detail because we have got a full chapter on data assimilation to study in this semester. Okay, as part of this subject. And then after the model is initialized, then we make the forecast. Okay, forecast for next 3 days or 5 days or 7 days or 10 days. Uh, and then from that forecast, we also store the 6 hour forecast to be used as a first guess for the next cycle, that is at 06 GMT. So again, next cycle, new observations come, they are analyzed on the model grid, they're further initialized or simulated, and again, we make a 6 hour forecast because the main forecast is done either at 00 GMT every day or at 12 UTC every day. Okay, the 10 days forecast, which we make operationally, whether in India or anywhere else in the world, that is either done at 00 GMT or 12 GMT. And rest of the time, model is just run for 6 hours because it requires first case is required for next cycle to begin. So for this 06 GMT, we will just run the model for 6 hours, and then output of that goes as a first case for the next cycle. And the same process is repeated here also. So like that, we go on to 18 UTC and make full 4 cycles, complete 4 cycles, 00, 06, 12, and 18 UTC. And then once we make 4 cycles of a simulation, then we assume that now the atmosphere, the theoretical atmosphere, is in balance with the model atmosphere, right? And then only we make the 10-day forecast, because unless the model is in balance, because data can give a lot of shocks to the model. We shall talk about all these things again and again in this semester. Now, raw data can give a lot of shocks to the model because raw data is not quality control. Now, there can be so many kinds of errors. And if we use the raw data directly into the model, then it will not obey the valid principles or well-known principles of the model, right? Like the law of conservation of mass, law of conservation of energy, law of conservation of entropy, and so on. So the raw data cannot be used directly, and therefore it has to be quality controlled and simulated in the model. So this is how the simulation cycle is done. So this is what is the past. So far in last 3 lectures, we have tried to review or summarize the history of the evolution of the NWP. So what is the future? Now, we shall try to summarize this also in today's lecture. The future, for example, yes, you can hear clearly? Are you able to
Yes,
hear?
sir. Sorry to interrupt, sir. Yes, sir, we can hear. Sir,
Okay,
Alok sir
so
is waiting
just
for
maybe another one
the
or two
next
slides
class.
and I will stop this class, okay? Okay, so the future,
Yes, sir.
detailed short range forecast using short scale models able to provide skillful prediction of severe weather. Okay, more sophisticated methods of data estimation, capable of extracting the maximum possible information from observing systems, especially remote sensors such as satellites and radars. Development of adaptive observation systems in which additional observations are placed, where ensemble indicates there is rapid growth. Ensemble forecasting is another important area of NWP. We shall talk about that later. Improvement in the usefulness of media-based forecasts, especially through the use of ensemble forecasting. Fully coupled atmospheric hydrological system, where the atmospheric model precipitation is downscale and used to extend the length of the river flows prediction. All these are applications for flood forecasting and so on. And more use of detailed atmosphere, ocean, land coupled models in which SST is predicted. Okay, we shall quickly now move because we have to go for next class. More guidance to governments and the public on subjects such as air pollution, ultraviolet radiation, transport, contaminants, which affects health, and an explosive growth of systems with emphasis on commercial applications of NWP, from guidance on the state highways to air pollution, flood prediction, guidance to agriculture, construction, etc. They are all the applications of NWP in different facets of the human life. Okay, so this is all is today's lecture, and with this we have completed the history of NWP, and we stop the class for today. There is no time for any question. If you have any question, then you can ask later. Okay, so I stop recording. Okay, and we can discuss more later. I will save the video, and after I will share the PowerPoint overview that you have and discuss later on the next class. All right.
So
Okay,
thank you,
sir.
sir.
So
Thank you.
we stop recording.
Thank you.